Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 6, Calculus Applications to Climate Science. In this video, we will create a visualization of the Newton's method and give some examples of higher order derivatives. Let's begin with section 6.4, Newton's method. First, we are going to create the Newton function. We're going to name this function Newton, and it will take f, which will be a function with default parameters TOL equal to 1e to the negative 12, x naught equal to 1, and n equal to 20. You can specify these parameters when you use the Newton function. However, if they are not given, they will default to these values. Once we enter the body of the function, we're going to define some extra parameters, hi, x1, and an empty array named p. We're going to enter this while loop, and all said and done, this will return a full p array, which will be the return value. Next, we are going to create a test function for the input of the Newton function. We're going to call this f. It's going to take one parameter, x, and it is going to return the cubed root of x plus 4 times the square root of x minus 10. Now, we are naming this variable root, and it will be the returned value from the Newton's method operating on function f with values 1e to the negative 12 as our value for total, x naught equaling 1, and n equaling 10. When we print out this solution, we do get this 7 iterations of the Newton method before we land on a root of 1.36 roughly. Figure 6.2 shows an illustration of the Newton's method. First, we are going to set up an x array evenly spaced between 0.2 and 1.7 with 30 digits. Then we're going to define a f function, and then we are going to define a g function, seen highlighted on the screen. We're going to start at x naught equaling to 1, x1 equaling to 1.45, and x2 equaling to 1.36. We are going to set up our figure and AX as a figure subplot. We are going to go ahead and suspend the frame so it does not show up on our plot. Now we are going to plot the data. First, we are plotting x by f of x. Then we are plotting the line space between 0 and 1.75 and a vector of zeros. Next, we are going to plot x by the y quantity f on x naught plus g on x naught times x minus x naught. Lastly, we are going to plot the x vector by the y coordinate f on x1 plus g on x1 times x minus x1. Both of these lines will be in a red dashed line. We are also going to add some scatter points to this plot to indicate critical areas on the plot. We're going to have the following scatter points. One at coordinate axis 1, 0, another point at x1, 0, another at x2, 0, yet another at x1, f on x1, and the last scatter point being on x naught, f at x naught. Now we're going to go ahead and create the appropriate tick marks on the x-axis. These two lines combined will make a vertical tick mark on the x-axis at the 0.5 value, and it will also give us 0.5 right at that tick mark. We're going to do the same sort of pattern for a tick mark at 1.0, 1.5, and 1.7. Next, we are going to add some line labels and text. We are going to add all of the following text to our plot. The first two parameters in the text function are the location of where you want your string to reside. The third parameter you see in the text function is the string that you want to set, followed by some size parameters and color parameters if you need it. Next, we are going to add some descriptive arrows to show the flow of the Newton's method. The first two parameters are your XY coordinate, where your base of the arrow is going to reside at. The next, third, and fourth parameter are described as the change of X and the change of Y. So these two parameters that are highlighted will give your arrow direction as well as magnitude. You could go ahead and change the arrow width and the arrow length to make the arrow head a little bit bigger or smaller. We are going to have 4 blue arrows appearing on our plot. Lastly, going through the plot parameters, adding a title, adding the X limit, adding a Y limit, and these 4 lines will help us set our axes to visible or not. We will not have a top, bottom, or right axes on our plot, but we will in fact set the default X tick marks to nothing because we specified them above in the highlighted text. Wrapping that entire block with a PLT show, we do get this beautiful illustration of the Newton's method for finding a root. You can follow the blue arrows from the initial guess, starting at x naught, to p naught, which is on our y function. Then from p naught, we go to x1, to p1, then to x2, and so on and so forth. We have these 2 red dashed lines indicating the tangent line through P naught and the tangent line through P1. Next, we are going to define a f function, and it is going to return the quantity x plus 1 to the 4th power minus the quantity of 2 plus x. We're going to go ahead and use our Newton method on this f function with n equal to 10. We do get these iterations of the Newton method to pop out, which converge to our root, which is 0.22 roughly. We are going to use the Newton method on our energy function. We do need to define some needed parameters. S equal to 1,365, EP equal to 0.6, and SG equal to 5.67 e to the negative 8. Then we're going to define that function for our energy. We're going to call it F3, and it is going to return the highlighted value, utilizing those defined parameters as well as an inverse tan. Then we are going to compute the Newton method for this F3 function using an x naught value of 220. When we print out this Newton iteration, we do get the highlighted text as our iterations. Then we are going to go ahead and compute those solutions for that F3 function once again, but using a different x naught value of 270. We can see starting at that x naught value, we do get these iterations to pop out. Lastly, using that F3 function once again with a different x naught value equaling to 300, we can print out the Newton iterations and we get a convergence on 289.14 roughly. Lastly, using that F3 function one more time and operating our Newton's method on it, we're giving it quite a low x naught value. And when we print out this Newton's iteration, it is quite longer than the other iterations that we did. And At the beginning, the first few iterations, it was wildly changing from 827 to 623, finally converging on a value of 289.14, roughly. Next, we're going to go to section 6.5, examples of higher order derivatives. The first and foremost thing that you need to know when computing derivatives in Python is that you need to define your symbols as symbols. That is what this highlighted text does. It sets our variable x to the symbol of x. So now we can run a differentiation function on a function, let's say x squared, and we do in fact get the derivative to come out, namely 2x in this case. In our next example, we are going to redefine x as the symbol of x, and we are making an e to the x function. Now we are going to differentiate the function of e to the power of negative x squared. This second parameter in our diff function just tells us which variable to take the derivative with respect to. We can see that we get the correct differentiation out of this function. However, it does convert our e parameter to the value of e. For higher order derivatives, let's go ahead and set symbols x, g, t, v naught, and h naught all as symbols. To take the first derivative, we're going to set our result equal to first derivative. Use that differentiation function on the function g times t squared divided by 2 plus v naught times t plus h naught. And we are actually going to take the first derivative with respects to the variable t. Printing out that first derivative, we do get negative gt plus v naught. For the second derivative, we are going to feed that differentiation function the first derivative result and then take the derivative with respects to t. We do get the second derivative of negative g. Taking the third derivative, we are going to input the second derivative into our parameter, into the differentiation function, and take the derivative with respects to t, giving us the third derivative of 0. This concludes Part 2 of Chapter 6, Calculus Applications for Climate Science. Join us next time for Chapter 9, Python Graphics for Climate Science.